Yeah, thanks for coming, everybody. My name is Ralf Wondratschek, and I would like to give you an introduction into kotlin-inject and how we use it in our project at Amazon. For context, I'm principal engineer. One of our core products is the software that's running in the electrical delivery vans. Amazon is refreshing their fleet, and they buy all these EVs from Rivian, and we write the delivery app that runs in there. If you ever sit in a Rivian van or car, they have this typical dual screen setup, and it's very similar in the vans. Last year, I was giving a talk here in San Francisco and also in New York where I explained the architecture that we use for our projects. Basically, I summarized how we manage our scopes and life cycles, our memory, and then how we implemented unidirectional data flow. The goal for us was to decouple our application more from the Android runtime because we've frequently ran into issues there. And this architecture worked quite well for us. It was quite successful. And in the recent 8-7 months, it became more apparent that we wanted to invest in Kotlin multi-platform. And we had this architecture that we developed for an Android runtime, but the goal was to decouple ourselves from Android. So it was a good exercise to see how far we can push this and bring this to Kotlin multi-platform. And it worked out quite well, but we had one big caveat. Core of our architecture was that we heavily relied on dependency inversion and dependency injection. And for that, we used Dagger as a DI framework and Anvil on top of it. And the problem with these two libraries is that they were written for Android and the JVM. So we couldn't bring them to KMP and then, for example, run the code on iOS. But at the same time, we really liked these frameworks. They were essential for us, for our architecture. They removed a lot of boilerplate. They made our setup easier. So we had to decide what we wanted to do. And the spoiler alert, the solution is kotlin-inject that we used. And I want to first explain again what Dagger does, what Anvil does, and then compare this to kotlin-inject, and then explain how we brought this further into our architecture and got the features back that we dearly missed. So just a quick reminder, Dagger 2 is pretty much, has 3 components. You have a provider side, you have an injection side, and the middle is this thing which they call a component. It's basically a hash map of your entire object graph. That's a way to think about it. Imagine you have an interface like weather repository with an implementation class. On the provider side for Dagger, you usually write a module, like this weather repository module. And then you have a provider method that says, whenever somebody asks for a weather repository, they get a weather repository implementation or an instance of this class. Then we also make this a singleton, and then Dagger will automatically cache everything for us in this scope. Then for Dagger 2, we need to set up the component. The component is really just an interface annotated with the add component annotation. We need to tell Dagger what it can provide. In this case, we include our weather repository module. We also need to give it a scope, so then Dagger makes more checks for us and ensures that we don't violate our scope hierarchy. And that's pretty much it. When we compile this code, then the Dagger annotation processor will generate a class called Dagger app component for us. We can use then this class to instantiate the app component at runtime. If we need to get an object out of our object graph, it's as simple as adding a single function to our app component, which we then can call on our app component instance, and then we get our weather repository instance. The example I showed you earlier with the provider methods, this can actually be improved. What we can do is we can teach Dagger automatically how to instantiate the weather repository input without the provider methods, and we do this with the inject function annotation on the constructor, and we also can move the scope annotation. And then we can transform this provider function into a binds method, and this saves us some boilerplate. Now, where I often see people struggle with Dagger is in a multi-module setup. So this example was very simple, and usually what we do is we put the component into the final application module, and that is necessary because the components, when Dagger compiles them, they have to know about all the features and everything that they have to provide and inject. So the best place for them is in the application module. With the weather repository module, it's easy. We can move this into our weather module in this example. But problems come up if we want to use something. For example, in the forecast module, we would like to get the instance of the weather repository and call this function on our app component. But this is not allowed because, again, this function only lives in the application module on the app component class. So we have a circular dependency. To solve this in a multi-module environment, it's actually fairly simple. What we can do is we can extract this function into a separate repository, into a separate interface, and then make our app component implement this interface. And then we can move this interface into our forecast module. And that's how we break the circular dependency and can scale Dagger through multiple modules. That's the basic setup for Dagger 2 and the most important thing, I guess, that you should understand. And on top of it, we used Anvil. And Anvil provides a bunch of extensions to Dagger 2. I gave a talk 2 years ago with my friend Gabriel here at droidcon SF. If you want to hear a deep dive about Anvil, I highly suggest to watch this talk. It covers a lot. But nonetheless, I want to give you a quick summary how we used Anvil in our project. So what Anvil does is it automatically allows you to contribute Dagger modules, for example, or bindings to a specific scope. And then it merges these contributions so you don't have to write all this code manually. So there's, for example, the contributes to annotation and the contributes binding. And going back, the way Anvil works, how it makes these connections is through a class reference. In this case, for example, the app scope. It's just a class. It's just a class reference. That's all there is to it. This is the code that we've written with Dagger 2. And what we can do with Anvil is simply say, contribute this weather repository module to our app scope. And then during the merge phase, Anvil will automatically pick this up. We can go even further and generate this binding method through Anvil by saying contribute this binding to the app scope. And then Anvil will generate actually the same method that you see here on the screen under the hood. And so with that annotation, we can get completely rid of this module. Now, we had this interface, the weather component interface. Again, we don't want to wire these things manually. All we have to do with Anvil, just say, contribute this interface to the app scope, and Anvil will do the rest. This is how our app component looked like with Dagger 2. With Anvil, it becomes a lot easier. First, we have to change the component annotation to the merge component annotation. We specify the scope, and what happens then under the hood is when Anvil sees this annotation, it finds everything that has been contributed to the app scope, merges it, and then generates actually the code that you see on the screen. Now, with that, we no longer need to add the module manually, so we can remove this. Actually, we can remove also the named argument, so it becomes even less code. Then we also contributed the weather component, so we removed this reference as well. And that's the result. It's much shorter, and everything now gets automatically picked up, so we don't need to do this wiring manually anymore. Anvil has other benefits. Besides that, it also improves build times. It makes our testing setup a lot easier because we can easily replace real implementation with fakes and mock data. It's very convenient. But the best part is that it's extensible, and we wrote a bunch of extensions for our architecture. So we wrote our own custom annotations that we use for certain classes that generate code under the hood, and everything then gets automatically picked up. So it's a really powerful mechanism. Now that I explained Dagger 2 and Anvil, I want to show you how this compares to kotlin-inject. But first of all, kotlin-inject is very similar to Dagger, and what I would call it is actually the Dagger 2 for Kotlin multi-platform. And this is not a threat. I know many people dislike Dagger 2 for its complexity, but I think kotlin-inject really took the good things of Dagger 2, removed the bad stuff, and it became a really nice framework. So in that sense, kotlin-inject is similar. It's again a compile time dependency injection framework, similar to Dagger 2. That means when you build your application, the framework will verify that your object graph is complete, that every dependency you provide can be provided, and every dependency that you request is part of the object graph. And that's a feature we didn't really want to miss. We know for Kotlin multi-platform, there's Coin and Codeine, but all these operate at runtime, and that's something we don't like, especially then in a multi-module setup with multiple teams contributing code. I think that it scales poorly. So we wanted to have those verifications run at compile time. It comes with a similar feature set. So all the good stuff you know from Dagger 2, like provider methods, scopes, qualifiers, multi-bindings, assisted injection, all of these features are there, and some of them are even improved by using the Kotlin language. But then it has more, like it supports Kotlin multi-platform fully, so we're not bound to the JVM or Android. Some of the things were removed, like binding methods and modules, and I actually think this is a good thing. And I'll walk you through this more in a second. But let's see, how can we convert the code that we have written for Dagger 2 now to kotlin-inject? First thing we have to do is we have to create a scope annotation. Kotlin-inject doesn't come with the singleton annotation for Dagger. It is there by default, but that it's not there is, again, a good thing, because usually you end up writing your own qualifiers and scopes anyways. So this was the code that we had for Dagger 2. With kotlin-inject, the first thing we need to update is the weather repository input. And all we have to do there is remove the inject annotation from the constructor and move it to the class. And it actually saves you one keyword and a few characters, so it's even shorter. The Dagger module has to be transformed. There, again, kotlin-inject doesn't have modules. What they decided to do instead is only to have interfaces and what they call component interfaces. So this weather repository module, we converted to a normal interface. We remove the annotation, and then we have to write a provides function. And it's very similar to Dagger. In this case, we just say whenever, again, a weather repository is requested, return this instance of weather repository input. And it functions very similar to a binding method. For completeness, I want to highlight that for kotlin-inject, they decided to provide two mechanisms. So both of these things are pretty much equivalent, this property and this function. We prefer using the function, even though it's a little bit more code and more characters. I think it's more expressive and clearly describes what it's doing compared to the extension property. But that's a matter of style. Both things would work. Now, kotlin-inject also has components similar to Dagger 2, and we can adjust the component that we've written here. Again, modules are gone, so we removed the weather repository, what we had. Instead, we had this interface. So we make our app component extend the weather repository component that we seen on the previous slide. But the rest stays the same. Dagger generated, the annotation processor of Dagger generated the Dagger app component class. Kotlin-inject instead generates an extension on the class. It's a little different syntax, but pretty much the same thing. And because it works, it's okay. Similar to the function to get weather repository out of our DI graph, kotlin-inject uses properties, same thing there. It's very similar. And then, as earlier mentioned, we can start now to decompose our component where we have the property. We can actually move this property to another interface and then make our app component extend this weather component. And then kotlin-inject will still generate all the necessary code for the property under the hood. And our diagram from earlier for our module structure stays the same. We still have the weather component, the weather repository component can stay in the weather module, and we have our app component. So I hope that showed you it's very, very similar. And I would like to now walk you through some of the good things that I really appreciated in this framework and were good changes in my opinion. All these annotations come from Dagger, they are all gone. So kotlin-inject doesn't have binding methods. There are no modules which got replaced by components. There are no subcomponents technically. for assisted injection, they decided to use lambdas and just a normal Kotlin language. So that was a really nice change. And this reduces the API surface. For Dagger 2, you often hear to complain that there are multiple ways to do a certain thing, and the outcome is always the same. And then you have to say, should we use this approach or this approach? It gets simpler and more direct with kotlin-inject. Arguments for components are very easy to implement. Sometimes you don't own an object and you want to provide it in your DI graph. On Android in particular, the example is with the application class, where the Android runtime creates your application, but you want to provide it in your DI graph. All you have to do really is adding a constructor argument to your component, and then the create function requires this as an argument, and you just pass it in. And it's very simple, and now you can start injecting the application class everywhere in your object graph. Component inheritance works similar. So with Dagger 2, you use subcomponents, and I know that they have another mechanism instead of subcomponents, component dependencies. And component dependencies are more similar to what kotlin-inject provided. But in our example, let's assume we have a second component, the logged-in component, which is technically a subgraph, or depends on the app component, and has a shorter life cycle. What we want to do here is, in the logged-in component, we want to allow it to inject everything that the app component does. And in kotlin-inject, it becomes just another dependency again that you add to the constructor. So our logged-in component in this case depends on our app component. And what then kotlin-inject will do under the hood is, again, update the create method. So you have to pass in the app component to the provider function when you instantiate your logged-in component. And that's all there is you have to do. Now you can, for example, start injecting the application object in the logged-in component graph. A pattern that we really like is when you have a subcomponent or a dependency on another component is we like to create a factory interface for the logged-in component, for example. And the argument here is, for example, that you have a user that you need to pass in from the previous example. Now, with this factory, we make the parent component implement this interface. So our app component starts implementing this interface. When you do this and try to compile then this code, kotlin-inject will complain because it says, oh, I don't know how to provide the logged-in component. I don't know how to instantiate this. There's a missing binding. And what you can do with kotlin-inject, and that's really nice and convenient, you can just overwrite this function. You can implement it yourself, and then kotlin-inject doesn't attempt to generate the code for you anymore, and it just works as you would expect. This is especially convenient in tests where you just overwrite a function, a provider, and you replace this with a fake maybe. So that's a really nice feature that Dagger doesn't support. And then there are other things where it leverages the default Kotlin language. For example, for lazy injections, it uses the normal lazy object from the Kotlin standard library. It supports default arguments. Sometimes you inject a type that's not provided by your DI graph, and then kotlin-inject would say, oh, there's a missing binding, similar to Dagger 2. But with kotlin-inject, you can say, oh, this is a default argument, and then it stops complaining about this. And then also, because it's built for Kotlin by default, I'm sure if you ever used multi-bindings in Dagger 2, you came across weird errors that the binding couldn't be found, and it had to do with parameter types, and then you had to add at random places the JVM suppress wildcards, and suddenly everything worked again, and Dagger was happy. This is really a non-issue. Again, kotlin-inject was built for Kotlin. Another benefit is that your build times get faster. So the way annotation processing works with Kotlin and Dagger 2 is when you build your module, the first task that Gradle will run is a task that is called stub generation. What it does, it takes all your source code in your module and it converts the Kotlin code to Java stubs. It will preserve the same API, but it will remove all the bodies from the function. But it's a partial Kotlin compiler iteration, so partial compilation. Then Gradle will take these Java stubs and run the Kotlin annotation processor. Then it will feed every Java annotation processor, and that's what Dagger 2 is. it will feed these Java stubs to the annotation processor. The annotation processor runs over Java code, and then they will generate code and spit out, in Dagger's case, more Java code. After this, Gradle will run Kotlin C. It takes the generated Java code from the annotation process together with your source code, compile all the Kotlin files into bytecode. And after this, it has to run Java C because there's Java code generated by Dagger 2, and it's an extra task when building your source code. With kotlin-inject, it gets easier. Kotlin-inject uses KSP, Kotlin Simple Processing, which is pretty much a replacement for annotation processing. And there, the setup is a lot simpler. So KSP, what it does, it takes the source code, runs a partial Kotlin compilation to build the AST, the abstract syntax tree, and then it feeds your simple processors with this AST, and you can iterate over the code, and we will see some bits later. You can analyze your code and then generate new Kotlin files. And once KSP is done, it will take the generated Kotlin code together with your source code and run Kotlin C. And then we are done. So there's no stub generation, there is no KPT anymore, and there's also no Java compilation anymore because kotlin-inject will generate Kotlin code and no Java, and therefore Java C becomes a no-op. But there are also some downsides where we think kotlin-inject could do better. And some of the issues that I will highlight now are already solved and hopefully will be released in the next version. But nonetheless, I want to call them out. We like the pattern in our code, in particular that's coming from Anvil, where we reuse scope annotations. For example, we have one single annotation for the singleton. And then we say through our class references, oh, this object is a singleton in the app scope. This object is a singleton in the logged-in scope. This object is a singleton in the presenter scope. So we don't have to redefine those scopes. Instead, we just create a new class reference, and this works pretty well with Anvil too. Kotlin-inject doesn't support this. Instead, you have to create a new scope annotation for every scope that you have. So our workaround was literally to create the add single in app scope annotation and the add single in logged-in scope. And we have to repeat this for every scope, which is quite tedious and is less consistent. The same thing applies for qualifiers, where we use the same mechanism. We have a single qualifier called forScope, and then we add these arguments to it. What we had to do for kotlin-inject instead is use type aliases. Kotlin-inject decided to use the Kotlin language, again, to implement qualifiers, which, in my opinion, is a bad choice. And they want to lift this restriction, and the next version will support qualifiers using annotations, which is very helpful, in my opinion. It makes the code more readable and avoids a bunch of boilerplate. Another downside is that the framework is still very niche. There aren't many projects out there using it. And it's risky when you want to build a new architecture, share this widely within your company, adopt it, you heavily rely on it. Usually a DI framework is still at the center of your architecture. And it's basically a single maintainer at this point. While she is very active and responds quickly, it's a risk. On the other hand, I also want to call out that it's open source. You can always fork the project if something is wrong or not maintain it anymore. And we were ready for this. In case this happens, we can continue maintaining it internally. But the support for Dagger 2, for example, is a lot higher. There are more companies using it. You can get more help online on Stack Overflow or somewhere else. Another problem with that, also single maintainer, the last release was 6 or 7 months ago. And since then, a lot of fixes went into kotlin-inject, and we ran into these issues, and we needed those fixes, so we had to fork the library internally, which is a little unfortunate. I want to walk you through some of the best practices that we follow in order to make the framework scale. And some of those advices now, they also apply to Dagger 2. For one, I mentioned that we put all the components into our application modules. And this has a good reason. Let's have a look at this example where we may have multiple applications. yes, we have to repeat these components over and over again in each application module. But what they do and which features they include and what code they generate is different. App 1, for example, only depends on the weather module, so it will generate code for the weather repository module. But it doesn't depend on the forecast module, so it doesn't know about weather component and will not generate the code for this, unlike App 2 and App 3. So I highly recommend put your components into the application module. It will make your DI setup easier. Scopes, we always put them on the class itself. You could also decide to put the scope annotation on the provider method, but we think it's better to make it clear to indicate that this class expects to be a singleton in a specific scope. So we always move the scope annotation to the class itself. Then the way we name these components is usually roughly what feature they cover or what they provide. And our provider function are literally prefixed with the provide keyword and then the type that they return. So that's roughly the pattern that we follow, and that adds a lot of consistency to our code bases. Then if you need to get an object out of the DI graph, we've seen this with the weather repository early, usually we make these components inner classes. And inner classes in these classes where they are being used. For example, here our view renderer needs the main coroutine dispatcher, so we created an inner class component, and so we keep it close to the usage side of things. So here we use the component, and then we can reference the dispatcher. And then for Kotlin multi-platform in particular, we decide to create a component for each platform, which is even more duplication, but it's very beneficial. For example, for the Android flavor of our common Kotlin code, we decided to create the Android app component. And here we provide the application class. The application class is Android specific, so you cannot reference it in common code. And instead of creating expect actual classes or workarounds like these, it's much easier to create a component per class. So we provide the application object in our Android app component, and then when Android code gets compiled, they can inject the application class like you would expect. And it's not somehow polluting the common code. We decided to do the same thing then for the iOS app component, and here we reference the UI application, which is the equivalent to the application class on Android. And now the iOS specific code can inject the UI application object. For the desktop flavor, there is no application class, so there's nothing that we have to provide. Then we went further and we repeated this also for all the subcomponents. For example, the logged-in component, there's then a specific Android logged-in component, and it references the Android app component. And we do this because then the Android logged-in component can also reference Android types like our application class. And then we had to repeat this for each platform. For iOS, we had a problem. So we decided to compile all the KMP code, all the KMP libraries into a single binary, into a single framework, and then this framework gets imported into Swift and Objective-C code. Now it happens that you have some implementations for your object graph that live in Swift code. And this is too late. When the framework gets compiled by Kotlin, we have to provide everything to the DI graph. And we cannot reference the Swift implementations then anymore. If somebody has suggestions for this, I'm open to hear. But the way we solved it is we introduced this single iOS native implementations interface, which is basically just forwarding all the cards to the implementation. And then we pass this single object to our iOS component, iOS app component. And then the interface looks roughly like this. It's just providing all the types that we know will be implemented in Swift and will be provided on iOS. So then for the concrete implementation of this lives in Swift, and it can instantiate the Swift objects. And when the Swift code then instantiates our iOS app component, it passes the single instance to our DI graph, and everything can be then provided also in the Kotlin code. The problem we then also quickly saw in our code base is that the boilerplate grew. So you've seen all these component interfaces, and you have to add them as a super type. So you will quickly see that your app component has one super type, Then there will be another component, another, and one more. Then there's a new feature, and there will be more components, components, and this list keeps on growing and growing and growing. It gets even worse when you want to introduce a new component interface or a new provider method, for example. We have a fairly modularized code base with multiple applications. So we have to add this interface, this new component interface, to our one Android application component. Then there's a second Android app where we have to add this. Maybe there's a demo app where we have to add this. The iOS app needs to be updated, also the desktop app. So we have to go through every single app in order to add this new interface, which is very tedious. And this is something that Anvil solved for us. We had to implement provider methods again, which were really just boilerplate for us. So it comes really down to that we started to miss Anvil a lot. And we wanted to fix that. So kotlin-inject uses KSP, and we wondered, okay, Anvil is not working. How can we get the same feature set? Can we implement Anvil for KSP and common code and kotlin-inject? And the key part here is that kotlin-inject supports multiple rounds, and that's what we needed. That's how Anvil works. Anvil generates a bunch of code before the Dagger annotation processor runs. The annotation processor then picks up the generated code and generates everything for you. So we decided, okay, let's give this a try with KSP. So we created a new project. Usually you have two modules, one module for your annotations, and then the compiler or the Kotlin symbol processor. I suggest you take a look at the docs if you want to set up a KSP processor. It's fairly simple and straightforward. So we have the runtime module with our annotations, our custom annotations, and then the Kotlin symbol processor. And the most important dependencies that you will have is probably Kotlin Poet in order to generate new Kotlin code, and then the Kotlin compile testing library to write your tests. I have to rush a little bit through this because I'm running out of time, but the docs for KSP are really great. Take a look at them. There's very little involved to set up a new symbol processor, and Google did a really good job there. So with that, we have our new symbol processor. The one thing I really would like to mention is when you write a symbol processor, don't throw random exceptions in your code and say, oh, something isn't working here, I throw an exception. It's not what I expected. Instead, use the logger, because when you use the logger, you can fail and actually point to the source code where something went wrong. And then if you have to fix issues in your code, it's a lot easier to detect where you must do this. Now, in order to implement kotlin-inject, we had two problems to solve. For one, we had to think about the API. We couldn't take the API directly from Anvil because of the way kotlin-inject works with scopes. It's a little different. We couldn't have these class references that we liked from Anvil, so we had to slightly modify the API. And the other is that we had to find all the contributions to a specific scope. For Anvil, back then, I used the Kotlin compiler APIs. That was easy. You can scan the class path, and we had to ensure that KSP, Kotlin symbol processing, provided a similar API. Now, on the API level, what we really wanted to do, if we wanted to add something to a scope, we wanted to add the contributes to annotation, similar to Anvil. But we had to specify the scope. So for our API, we decided to simply add a scope, like the add singleton annotation. And that worked well enough for us. For the app component, we had to make, unfortunately, a few more changes. First of all, we had to add a new annotation, add merge component. Anvil has the same, but it then also generated more code under the hood because it could modify source code, whereas with KSP, you can only generate new source code. But it wasn't a big deal. What we decided to do is generate a new interface, which we call the merge component, and that's a one-time thing that you have to do. You have to add this super type. But the merge component combines everything that we contribute. The second problem is that we need this class path scanning. Unfortunately, KSP provides an API for this. It's called get declarations from a package, so you can look up all the declarations in a specific package. And this was good enough for our use cases. This is roughly how the algorithm works. Imagine you have two components that you contribute. Then our symbol processor eventually will see in a module the merge component annotation. Then it will go ahead and generate this app component merge that we've seen earlier. it will add these component 1 and component 2 as super types. Then we update our app component with that, and this will make kotlin-inject generate all the necessary code. And once we're done with that, we want to run the simple processor. And this is supported because KSP supports multiple rounds, and kotlin-inject out of the box supported this properly. So this is an example. Imagine this is a class that we have, the weather component, and this is the code we want to generate. And Kotlin, KSP again, makes this very simple. The APIs are so simple and easy to use. It's a really nice entry point for meta programming. This is roughly how it looks like. This is very little code. It's almost really what we run in production, so straightforward. The point here is that we find all the contributed classes, and then we generate this component interface in this special package where we later will look up the code. This is standard Kotlin poet code. It's straightforward, and that's all there really is. The one thing I like to highlight, KSP supports incremental compilation, but you need to assist it and teach KSP about the relationships. So if you have a source code file, this will trigger creating this generated source code file. So you have to create this mapping. But other than that, straightforward. Then we had to write some tests for it. This is inspired by how I wrote the tests for Anvil back in the day. Very readable. There's a trick that I like to use, Kotlin compile testing. The library that is used under the hood is pretty neat because it runs the Kotlin compiler under the hood for you, and then you can use the class loader to load the code. The merge component, I go quickly through this, but it's very similar to the example with contributes to. All we have to do, we have to wait for when we see the merge component annotation, then we find all the contributions, we check that they have the right scope for what we expect, and then we create a new interface using Kotlin poet, write the source file, again, make the connections for incremental compilation, and that's pretty much it. Then that's all we really needed to do. On top of it, we implemented other annotations like contributes binding and subcomponent, but we got all the Anvil features back that we needed. So this is the original code that we had with our custom extensions for Kotlin-inject. It became like this, very similar to Anvil. Our original weather component got boiled down to this, and everything now automatically gets compiled and generated, and we no longer have to update all these classes, create this huge list of components that you have to implement, and it all just works. If you want to take a look at this, there's a discussion going on in Kotlin-inject. We hope we can open source these extensions because I think they make this framework even more powerful. And that's pretty much it. In short, KSP is great. Use it. Think about creative ways how you can extend your existing frameworks with it. Usually you find everything you need. Kotlin-inject is great, and it's improving in the future. We can highly recommend using it as a Dagger replacement in KMP projects and common Kotlin code. And yeah, thanks for coming.